Well, hi everybody. I'm Anton. I'm coming from Toronto. Opus One Solutions is where I work. So just before I get started, a bit about me. So I have a background in electrical engineering. I did a master's in power systems, computational algorithms. That's where I got into Python a little bit, but more in an academic setting. So my code was not good. Please don't ask me what it looked like. And I also spent 2 years working in the rooftop commercial solar industry in Ontario. So also about Opus One Solutions. So we're a power systems company based in Toronto. We're trying to build software to help utilities do distribution analysis on their grids. So not like transmission systems, like high voltage, but like we're thinking about the wires you would see on the street. That's what we're trying to deal with. And we're trying to help utilities do figure out what's happening on their grid, do real-time operations, and also control like renewables and batteries and that kind of stuff, which are things that are not really on the grid too much right now, but they're starting to be a big thing. We're also trying to do locational price forming, which is like trying to figure out how much value distributed solar, for example, or wind could bring to the grid. And we're also trying to help utilities figure out where they should put those kind of assets in the future. So we're really focused on trying to get utilities to adopt renewable energy, and we're trying to use software to do that. And we're using Python to do that, so that's pretty cool. So my talk is about testing and how you can write good tests, and hopefully it's going to be a bit of a case study in what we did to make our tests a bit better, a bit more readable, and hopefully you guys get something out of it. So the problem that we had, so we wrote logic to analyze power networks. We wanted to assert things about the network structure of the power grid. We wanted to look at attributes of individual elements in the network, so whether it's a power line, we wanted to know its resistance, or a generator, we wanted to know how much power it could put on the network. And we want to do math on the network, so analyze it and come up with like statistics about the network and figure out how it's going to operate. And we want to do all this using test-driven development. So as some of you might know, writing tests can be hard. Sometimes your data is complicated, and ours is one of those cases. And your tests have to be well designed, just like your code. Otherwise, they're hard to maintain and they're hard to understand. So I'm going to do a bit of a dive into power systems and into object models. So there's no test on this stuff, but just to give you an idea of what it looks like and why we wanted to simplify things. So here's a sample network. So you got two nodes, A and B, and we got a line in between it. This is what the simplest you can get for a power system. And there's 3 dashes there, which say that it's a 3-phase line. I'll explain more about that in a second. So in power systems, we call these buses, and that goes back to like the bus bar terminology, which is a computer science term, but it's also used in power systems. And a branch is what connects them. In network speak, those are called nodes and edges. And so the network thing's going to come back quite a bit. So what does this look like in real life? So here's a picture of a power system close to my house. So it's a distribution line. So this is like the high voltage. It's probably between 25 kilovolts and 44 kilovolts. So that's high voltage for distribution, but it's like low voltage for like transmission systems. So that's the kind of power lines you'll see. I've seen them around Montreal. They're pretty much all around the world. You'll see stuff like this. So that's a line. And then in the middle, you see these 3 kind of cylindrical cans. These are transformers. So this is what we would call a node. So you have a line, 2 segments of line that meet here, and then you have a device tapping off. So that's a node, right? So that's where we get our network topology. So you might think one of the nodes might be where those transformers are, and you have a line going off, and then somewhere else there's maybe another node. So that's kind of the basics of power systems for you. So what about the data model? So I want to represent that power system using SIM, which is an international standard for using XML to describe power systems networks. It was designed by power systems engineers, as you can imagine, not software engineers. And so how complicated could that really be? Well, let's get into it a bit. So we got node A and node B, and these are modeled in SIM as connectivity nodes. So you can see we have 2 XML objects here, which are connectivity nodes, node A and node B. And then we have an AC line segment, which is the line that goes between them. And that has an attribute, so it's a length 600 meters. So that's like the very basics. But what else could we have? So as you saw in that picture, the line actually has 3 lines in it. So those are for the different phases. So they're 3 different waveforms, so we call it one line. So here's a bunch of AC line segment phases objects, which represent those. So there's 3, A, B, and C, and then there's also N, which is like the neutral ground line that comes back and returns any current that might be coming across that line. So that's a bunch more XML for you. Then the lines are actually in this object model. They're connected to the terminal or to the nodes by terminals. So we've got 2 more terminals. So that's a bit more information for you. And then Finally, to have this be a real power system, they have to be inside a feeder, which is kind of a grouping of lines and nodes, and so we got that. So putting that all together, here's our basic bare bones sim XML, and it's 40 lines. So it's a lot of code. It got out of hand pretty quickly. If you're feeling gross about this, all this XML, like I feel gross about it too. it's not nice, and we didn't like it very much. So say we want to do a simple test. So here's a nice simple test. So I've got test 3-phase line sim model, right? And I got my XML network. It's described in a string with a bunch of objects. I truncated it a bit because otherwise it won't fit on this slide. And then here's my test. So assert AC line segment is in the XML network. So that's like the simplest test. I made my own little test library so that it would work in Jupyter. So that's what this from whatever, and I can run that, and you can see the test pass. So that's great, right? But what's wrong here? So our test is hard to read. So if we go back to here, we've got a pretty simple assertion that we're doing. It's pretty obvious what we're trying to do there. But the data that goes into it is like, there's a lot there. And if you don't know how to read it, like you look at that and you think, I don't know what we're testing for. I don't know what's going into this test and why it might pass or fail, other than the fact that you can see AC line segment. So you guys are quick. So another big problem is that new tests are a lot of work to write. So let's say we wanted to make a line that was node C to node D. Like now we have almost the same XML, but we have to change some labels. What if we wanted to add some other, like a solar panel or a generator or a transformer? All kinds of different objects we might want to add to it and test. And for each of those, you have to make a nice big XML snippet. It's a lot of work. If you don't know this model, you're going to run into trouble quickly. So we came up with a quick and dirty solution, which is to use docstring pictures. So we started adding documentation to our tests. So here's that same test, and you can see I've added a docstring at the top, which is just like, you can read that before you read the test and see what the network is supposed to be. So we're testing a simple two-node network that looks like A dash 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 B. And then below it, there's the XML snippet, and you just have to kind of know that the diagram that we drew there is also described by this XML. And the test passed, which is great. So we can show you also a more complicated network. So say this has 5 nodes in it. So that's about 600 lines of XML. So you can see the problem. This would be a pretty long and impossible to read test. You have to scroll down one file per test basically, and then all you're doing is that one assertion. It's not nice. But we have docstrings, so you can know what the network is. So how did we do? Well, tests are harder to write because now we have to make that XML and we got to make a diagram, right? It's still hard to reason about what the data represents because we have a diagram, but really if you want to know what's wrong with your test or what's right about it, you have to read that XML anyways. And now we have to maintain docstrings. So if you added a new feature and now you had to add another object to your XML, now your docstring might be out of date. And there's no test that's telling you that. So they might be out of date. You can't really trust them. At the end of the day, you still have to read all that XML. So another quick idea we had, what if we put that snippet in a file? So here's an example of what that looks like. So we put all that stuff in XML network.xml. We read it, and then we just do assertion. So now the test is nice and short, but it's not perfect. Now our docstrings are even harder to maintain because they're not in the same file. And the tests are still hard to write because you still have to write all the XML. And now we have a bunch of files in version control. So what if the diagram is the test? So that's what we did. So we built the library called ascii-sim, and now we have a diagram, node A dash dash dash. We have ABC, which is a label for the line, and node B. And we're making XML. So there's no XML files, there's no snippets that I've truncated. This is the whole test. We're doing the same thing, and it works. So it's a bit simpler to read. So what are we? And here's an example. Runs off the page, but that's the XML that's generated by that call to XML from ASCII. So how does this work? Well, first of all, we have a library called ascii-graph, which is a library we wrote in open source, and it parses a diagram of text, ASCII text, into networks. So you can get a generic network structure. It figures out the length of each line based on the number of characters in the line, and it includes the position of each node, like in the kind of 2D string, ASCII string, and it adds labels for each of the lines. So here's an example of just a node, or 2 nodes and a line, and we've got a network. It's a NetworkX object, and it has N1 and N2 for the nodes, and then it has one edge, which is a tuple N1 and N2. Here's a more complicated example. We've got some labels on there, on the lines, and you can see we have A, B, C, D, E, F, all these nodes, they have positions, and we have all these edges, and the ones that have labels that show up in our data structure. So that's kind of nice. So graphs are cool. ASCII graph gives us a NetworkX graph, which is another open source library. If you do any network stuff, you should check it out because it has a lot of features. So for example, we can do NetworkX.shortest path on our graph, and we can see that ABCF is the shortest path from A to F. We can also do shortest path with a weight, and it will take into account the length of the lines. So here's a funny, weird thing. ABDEF, CF is a shorter path in this case, which is weird based on this diagram, but it is shorter because fewer characters in those lines. What else can we do? So we can get the neighbors. So we can get neighbors of B, and it gives us ACD, and neighbors of are non-neighbors of B. So that's kind of handy. And then we can also draw stuff. So this is like NetworkX gives you kind of like it just makes a randomly generated. So if I run this code again, it will give you a different shape, but you can graph them. So that's kind of cool. So on top of that, we built a library called ascii-sim, which is a library we use for our tests. So it turns those networks, those NetworkX objects, into power system stuff. So it makes XML objects, or it makes objects that we can that represent the power system. So those edges we showed you, they become lines. There's nodes where those edges meet. The labels on the lines, they indicate the phase on the line. So here's that example, N1 and N2. So these become those connectivity nodes that I told you about earlier. We've got one line which is between them, and ABN tells us the phase. So that's the number of wires that will be in that line, in that picture I showed you. So that's kind of nice. And it also makes up some realistic properties for us. So one line, one character in a line will correspond to 100 meters. So this, for example, is like a 10-character line, so it would be like a 1 kilometer power line, which is cool. And we also mapped our graphs onto real coordinates, so we can pull this network up in our UI for our product and see that it looks right, and we can test UI features with that stuff as well, which is really nice. So we can also interpret the node labels to get some cool power system stuff. So for example, S is where you get your power from the high voltage transmission system. If you ever see like a place with all kinds of big metal objects and huge utility things coming together, that's a source or a substation. You can also make loads that might be like a factory or your house, and it's pulling power off the grid. We can have PV, which is a solar panel, so that's generating power and putting it on the grid. And we can use these curly brackets to represent a transformer, which is going to step your voltage up and down. So we said, I showed you those cylindrical objects in that picture. Those are transformers, and they just step your voltage from whatever that higher distribution level voltage is down to something that you could safely like plug into your house without having to have someone with lots of training work on your whatever your panel. So here's a diagram of what that stuff looks like. So we've got a source, that's where all the power is coming from the transmission grid, and we've got two transformers stepping down so that we can service loads and get power from generators. And we also have a switch in here. I didn't show you guys that earlier, but you can also have a switch, and you can say whether it's closed or open, and that is going to affect how power flows through this network. So we can also pass in some key settings for devices, such as the voltage of a transformer, the power demand of a load, or the power generated by a solar panel. These allow us to do test our power systems logic that we're writing. So if we, for example, implement power flow, which is going to figure out how current flows on a network, we can add a generator, and we can see that the power flow changes, that kind of stuff. So here's what that looks like. So you can see I've got source. I've set the voltage at 13.7 kilovolts. I've got two transformers, and they both step down from 13.7 to 4 kilovolts. And then I've got a load, which is consuming 20 kilowatts, and a PV generator, which is making 50 kilowatts. So that's what distributed generation looks like, by the way, having PVs and loads in the same spot. And that's the kind of thing we're trying to test and figure out how we can analyze. So this is enough information basically to do power flow, which is the holy grail of power systems engineering. And then finally, we map this onto a map. So this is a picture from our product, and that's that same grid, and it's kind of superimposed near our office, which is in downtown Toronto. And so you can get an idea of what that looks like, and you can test the more UI features of our product, which is nice. So what have we accomplished? So tests are self-documenting, right? So from my perspective anyways, as a power system engineer, I look at this diagram and I say, oh, I know exactly what that is. I know exactly how it should behave as a network, and I can do tests on it. What else? We've made it much easier to dream up new tests. So I don't know if you noticed, but like the first example of ASCII sim stuff I gave you was like 2 nodes and a line, and we worked our way up to having a bunch of transformers and adding PVs and loads. And so one of the things we recently did was we started modeling batteries, which is another like up and coming renewable energy device that people want to do on the grid. And so we built that, and then we made something in ASCII sim to make batteries, and we could right away write a whole bunch of test cases. Like, what if the battery's charging? What if it's discharging? What if it's making imaginary power? What if it's making real power? You think I'm joking, but imaginary power is a real thing. And we can also parameterize our tests. So here's an example. We're testing the number of phases in the network. And I can use PyTest to parameterize this and write in different phase labels. So now I have like 8 tests that test all the different configurations of a power system. And I can make a network, and I can do stuff on it and see that the results are what I expect them to be. So now we have a lot of tests. It's really concise. And it gives you an easy introduction if you're new to our code base. If you're a power systems engineer, you can look at our diagrams and say, oh, I kind of know like what that would be. And if you're not a power systems engineer, you can look at what it produces and work backwards and figure out what it is. So that's kind of nice. So the takeaways, so good tests require good tools. So this is a tool that we've used a lot internally. It's allowed us to write more tests that are easier to troubleshoot when we break them. You can figure out, like, is the test just a bad test that I need to make it more detailed, or did I actually break something really bad? So that's been really helpful. We write a lot more tests that way. So testing is a design problem, not a chore. So we found especially that like we have to spend time code reviewing and testing, like doing a good job writing our tests as well, because they need to be able to maintain them. And this has really helped us to do that. And then lastly, that pet idea that you have just might be a good idea. So yeah, that's all I have. So if there's any, I could take a couple questions. Go ahead. Yeah, so you could probably draw a network that was like a neighborhood before you got like, you know, too big and like too hard to, like it's when it becomes like a big 2D diagram, it's hard to make that in ASCII. But so we use this a lot more for unit tests and like just add a couple devices and see that they act how they should. But obviously like the grids that we're doing in real life are like, you know, a whole neighborhood, like a large neighborhood, or like a small city. And those kind of things you can't draw with this, but like we're really using this. It started at doing unit tests, and then hopefully, you know, depending on what our customers' data is like, maybe you'll be able to like scale that up and put in their data, and it'll do the same things that you're expecting. But that's right. So, question. Yeah, so we're not using MATLAB, but we are using a similar tool called GAMS, which is it's just like it's called General Algebraic Modeling System. So it's just a language for doing algebra problems. So we're writing minimization programming in that language, and then so we can actually take these networks that I've been drawing, and like there's like 1 or 2 things you have to do them to make them like easy for that to consume, but then you can go and put them into that package, and you can run PowerFlow, and you can do optimization problems. You can do just straight up PowerFlow. You can do time series stuff. You can do all the crazy math you want, and you can get out objects. So we kind of built this. We've been kind of iterating on it and getting to the point where we can now make networks and then run PowerFlow on them and see like, did this electrically do what I expected it to do? And so that's been a really nice way to do tests for us. Yeah. Yeah. And any other questions?